Every single day, thousands of commercial flights take off and land without incident, and most passengers never think twice about what's happening outside that thin aluminum shell at 30,000 feet. But there's a scenario that aviation engineers have been obsessing over since the very first jet engine took to the skies. One that sounds almost absurdly simple, and yet has shaped the design of nearly every turbine engine flying today. What happens when a bird flies into a jet engine? Welcome to This Is Why Engineering. If this is your first time here, hit subscribe. This is exactly the kind of question we answer every week. Now let's find out. The answer, depending on how you think about it, is either completely catastrophic or impressively controlled. And the reason it tends to be the latter is one of the most quietly remarkable stories in engineering history. First, let's understand what a jet engine actually is at its core. At the front, there's a massive spinning fan, sometimes over 2 meters in diameter, rotating at hundreds of kilometers per hour. Behind it, air is compressed, mixed with fuel, ignited, and blasted out the back. The whole process happens in a fraction of a second, continuously thousands of times per minute. It is essentially a precisely balanced machine that moves enormous volumes of air at violent speed, and it does this while tolerating vibration. Temperature swings from -60 degrees to over 1,000, and the stresses of takeoff, cruise, and landing, day after day, for decades. The margins are engineered to be extraordinary, which makes you wonder, what does a 4-kilogram goose do to all of that? The physics are actually brutal. A bird weighing 2 kilograms, struck at a closing speed of 300 kilometers per hour, hits the engine with the kinetic energy equivalent of a car traveling at city speed. That energy doesn't disappear. It has to go somewhere, and it goes directly into the fan blades, those precisely shaped, incredibly thin aerofoils spinning at thousands of revolutions per minute. In a worst-case scenario, a large bird can shatter a blade, and that fragment then becomes a secondary projectile inside the engine. It hits the next blade, then the next. In aviation, this is called an uncontained failure, and it is the scenario that engineers spend the most time trying to prevent. But here's where it gets interesting. The reason most bird strikes don't end in catastrophe isn't luck. It's the result of decades of deliberate, systematic, almost obsessive testing. Every commercial jet engine must pass what's known as bird ingestion certification before it ever powers a passenger aircraft. And this testing is exactly as extreme as it sounds. Engineers use compressed air cannons, essentially large guns, to fire dead birds into running engines at realistic speeds. They test single large birds. They test flocks of small birds simultaneously. They test the engine's ability to absorb the impact, contain any damage, and either continue running or shut down safely without sending debris through the fuselage. The FAA and its international equivalents require engines to survive these tests under strict controlled conditions, and the tolerances are extraordinarily precise. What engineers discovered over decades of this work is that fan blade design is everything. Modern fan blades on high-bypass turbofan engines, the kind on every large commercial aircraft, are not made of simple metal. They're hollow titanium structures or increasingly carbon fiber composites layered and bonded in ways that allow them to deform and absorb energy rather than shatter and fragment. The goal is something called graceful degradation. The blade bends, it distorts, it may even break, but it breaks in a way that the engine can tolerate, and critically, in a way that doesn't turn the blade into shrapnel. The engine then vibrates, triggers sensors, and the pilots get an alert. The engine is shut down. The aircraft continues flying on its remaining engines because that redundancy has been there from the beginning. This is also why modern aircraft are designed with multiple engines positioned far apart on the wings. A single bird strike that takes out one engine is, in the vast majority of cases, a manageable event. The aircraft was already designed to take off, fly, and land safely with that engine inoperative. Every pilot trains for it. Every aircraft is certified for it. The engineering assumption is not that bird strikes won't happen. It's that they will, regularly, and the system must survive them anyway. The statistics back this up in a slightly uncomfortable way. Bird strikes are not rare. The FAA receives tens of thousands of strike reports in the United States alone every single year. Most are minor. A dent in the nose cone, a smear on a windshield, a small bird swallowed without consequence. But the number of serious incidents involving large birds or flocks near low-altitude flight paths during takeoff and landing is significant enough that airports maintain active wildlife management programs. Falconers are employed at major airports. Grass is kept deliberately short or long depending on which bird species it discourages. Radar systems track bird flocks in real time near runways. Both lost thrust almost completely. The crew had less than 3 minutes and no viable runway within reach. Captain Chesley Sullenberger and First Officer Jeffrey Skiles executed a water landing on the Hudson River. All 155 people on board survived. The aircraft floated long enough for ferries and rescue boats to reach every passenger. It was called the Miracle on the Hudson, and it was genuinely extraordinary, but it was also the outcome of an enormous amount of engineering, training, and certification work that made it survivable. The aircraft glided predictably because the airframe was designed to. The pilots knew exactly what to do because the scenario, however unlikely, had been trained for. The passengers survived because the seats, exits, and evacuation procedures had been tested and refined over decades. The edge case that still concerns engineers most. Work since 2009 has focused on improving engine resilience to large bird ingestion specifically, updating certification standards, and refining wildlife management around airports. There is something almost philosophically interesting about the way aviation handles this problem. The bird is not going away. Birds were in the sky long before jet engines, and they will be there long after. The solution is not to eliminate the hazard. It's to build systems robust enough that the hazard, when it inevitably arrives, cannot bring the system down. That philosophy runs through every part of commercial aviation, and it's why, despite what the statistics about bird strikes might initially suggest, flying remains the safest form of long-distance travel ever devised. The engine didn't need to survive every bird. It just needed to be engineered well enough that when it met one, everything else could keep going.